The Boötes Void spans 330 million light-years across. That's roughly 2 billion times the distance from Earth to the Sun. To put this in perspective, if our entire Milky Way galaxy were the size of a coin, the Boötes Void would stretch across an area larger than a football field. Within this incomprehensible volume of space, where we would expect to find 2,000 galaxies based on the average density of the universe, we find only 60. The void is so empty that its density is just 10% of what cosmologists consider normal for cosmic space. Chapter 1. Cosmic Desert. The story of the Boötes Void begins not with its discovery, but with our fundamental misunderstanding of what empty space actually means. When we look up at the night sky from Earth, we see a universe that appears uniformly populated with stars, planets, and galaxies. This observation led early astronomers to assume that matter is distributed relatively evenly throughout the cosmos. The Boötes Void shattered this assumption so completely that it forced us to rebuild our understanding of cosmic structure from the ground up. To understand why the Boötes Void is so extraordinary, we first need to grasp what cosmologists consider normal for the universe. When astronomers map large-scale cosmic structure, they discover that galaxies aren't scattered randomly through space like grains of sand on a beach. Instead, they form an intricate three-dimensional web of filaments, walls, and clusters separated by regions of lower density called voids. This cosmic web resembles a vast soap bubble structure where galaxies collect along the bubble walls, and voids represent the empty spaces inside the bubbles. In a typical cosmic void, and there are millions of them throughout the observable universe, the density of galaxies might be 20% to 50% lower than the cosmic average. These standard voids span perhaps 20 to 50 million light-years across and contain scattered galaxies that formed when dark matter halos managed to accumulate enough mass despite the void as low-density environment. Astronomers have cataloged thousands of these conventional voids, and they fit comfortably within our theoretical models of how cosmic structure evolved over the 13.8 billion years since the Big Bang. The Boötes Void operates by entirely different rules. Officially designated as the Boötes supervoid, it spans approximately 330 million light-years in diameter, roughly 6 times larger than typical voids. Within this enormous volume of space, galaxy density drops to just 10% of the cosmic average. To put this in perspective, if you could shrink the entire observable universe down to the size of Earth, the Boötes Void would represent a region the size of the Pacific Ocean that contained almost no matter whatsoever. The mathematical implications of this emptiness are staggering. Dr. Andris Kovacs from the Eötvös University in Hungary, who led comprehensive studies of the void's properties, described it as the largest and emptiest known structure in the universe. But the void's extreme nature goes beyond mere size and emptiness. Computer simulations that successfully reproduce the cosmic web's overall structure consistently fail to create voids as large and empty as Boötes. The most sophisticated dark matter simulations, running on supercomputers for months at a time, can occasionally produce voids approaching Boötes size or emptiness, but never both characteristics simultaneously. This simulation problem reveals something profound about our understanding of cosmic evolution. The mathematical models we use to describe how galaxies, dark matter, and cosmic structure formed over billions of years are incredibly successful at predicting most features of the universe we observe. They accurately explain galaxy clusters, cosmic filaments, the cosmic microwave background radiation, and thousands of smaller voids. But they struggle to explain how nature carved out a region like the Boötes Void without violating the fundamental physics of gravitational collapse and structure formation. The void's discovery in 1981 by Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman represented more than just finding a new cosmic object. It marked the moment when astronomers realized that the universe contains structures so extreme they challenge our theoretical frameworks. The team was conducting the Center for Astrophysics Redshift survey, systematically measuring distances to thousands of galaxies to map large-scale cosmic structure. When they plotted galaxy positions in the direction of the constellation Boötes, they found something unprecedented: a vast spherical region containing almost no galaxies whatsoever. The technical designation supervoid reflects the object's extreme properties compared to ordinary cosmic voids. While regular voids might contain 50 to 200 galaxies per cubic megaparsec, the Boötes Void contains fewer than 20 galaxies per cubic megaparsec, a density so low that if you could magically transport Earth to the Void's center, the nearest galaxy would be approximately 150 million light-years away. For comparison, our nearest major galactic neighbor, Andromeda, sits just 2.5 million light-years from the Milky Way. This isolation has profound implications for any hypothetical civilizations that might exist within the void. Without nearby galaxies to study, astronomers in such a location would have developed radically different theories about the universe's nature and evolution. They might have concluded that galaxies are extremely rare phenomena, or that the universe is much smaller and younger than it actually is. The cosmic microwave background radiation, the afterglow of the Big Bang that provides crucial evidence for our understanding of cosmic evolution, would still be detectable, but interpreting its significance would be far more difficult without a rich galaxy population to study. The Boötes Void also challenges our understanding of how cosmic structure emerges from quantum fluctuations in the early universe. According to the inflationary Big Bang model, tiny quantum variations in the density of matter and energy were stretched to cosmic scales during the universe's first fraction of a second. These density variations later grew under gravitational influence to become the cosmic web we observe today. But creating a void as large and empty as Boötes requires an initial density fluctuation so extreme that it borders on the statistically impossible. Modern observations using advanced telescope surveys have refined our understanding of the void's properties while deepening its mystery. The Sloan Digital Sky Survey, which has mapped the positions of millions of galaxies across large portions of the sky, confirmed that the Boötes Void represents the most extreme underdensity in the local universe. Subsequent studies using the 2-micron All-Sky Survey and other deep galaxy catalogs have verified that the void's emptiness extends across multiple wavelengths of light and isn't simply an artifact of observational bias. Perhaps most intriguingly, the void appears to have influenced the cosmic microwave background radiation in ways that shouldn't be possible according to our standard theoretical models. This radiation, which fills all of space and represents the afterglow of the Big Bang, should be extremely uniform across the sky. But in the direction of the Boötes Void, astronomers have detected a subtle but significant cold spot that suggests the void's gravitational influence extends far beyond what conventional physics predicts. The existence of the Boötes Void forces us to confront an uncomfortable question. If our theories of cosmic evolution can't explain how such an structure formed, what else might we be missing about the universe's fundamental nature? The void represents a cosmic stress test for our understanding of dark matter, dark energy, and the laws of physics themselves. It's a natural laboratory where the normal rules of cosmic structure formation appear to break down, offering us a unique window into processes that operate on scales so vast they dwarf anything we can study in terrestrial laboratories. As we continue exploring the mysteries of the Boötes Void, we'll discover that this cosmic desert represents far more than just an empty region of space. It's a key to understanding how the universe achieves structure on the largest scales, a challenge to our most fundamental theories of cosmic evolution, and perhaps a glimpse into the deeper principles that govern reality itself. The void's very existence suggests that our universe is far stranger and more mysterious than we ever imagined, and that the spaces between galaxies might hold secrets as profound as the galaxies themselves. Chapter 2. Impossible Mathematics. When Cosmologists first attempted to calculate the probability of the Boötes Void's existence using our best theoretical models. They encountered results so extreme, they initially assumed computational errors. The mathematics behind cosmic structure formation, which successfully explains virtually every other large-scale feature of the universe, breaks down when confronted with the void's extraordinary properties. This mathematical impossibility represents one of the deepest challenges to our understanding of how the universe works. To understand why the Boötes Void is mathematically problematic, we need to examine how cosmic structure forms according to the lambda-CDM model, our standard theory of cosmology. This model describes a universe dominated by dark matter and dark energy, where all cosmic structure grows from tiny quantum fluctuations that emerged during the inflationary period immediately after the Big Bang. These initial density variations, preserved in the cosmic microwave background radiation, provide the seeds from which all cosmic structure eventually grows. The process of structure formation follows well-understood mathematical principles. Regions with slightly higher density gradually attract more matter through gravitational attraction, growing into cosmic filaments, galaxy clusters, and individual galaxies. Regions with lower initial density become voids as matter flows away toward higher density areas. This process is governed by precise equations that relate the initial fluctuation amplitude to the final structure size and density contrast. Dr. Benjamin Wandelt from the Institut d'Astrophysique de Paris led comprehensive studies calculating the statistical likelihood of finding voids with the Boötes Void's extreme properties. His team's calculations, published in the Astrophysical Journal, revealed that producing a void with both the observed size and emptiness of Boötes requires an initial density fluctuation so rare that it should occur only once in every 400 comparable regions of space. Given that our observable universe contains approximately 100 regions the size of the Boötes Void, finding such an extreme structure represents a 4,000 to 1 statistical anomaly. But the mathematical problems run deeper than simple statistical rarity. When cosmologists model void formation using unbody simulations, computer programs that track the gravitational evolution of millions of dark matter particles over billions of years, they consistently fail to reproduce the Boötes Void's properties. The Millennium Simulation, one of the largest and most detailed cosmic structure simulations ever performed, tracked over 10 billion particles through 13.8 billion years of cosmic evolution. Despite its enormous scope and computational sophistication, it never produced a single void approaching the Boötes Void's combination of size and emptiness. The mathematical framework describing void formation includes several key parameters that determine how large and empty voids can become. The most important is the linear growth factor, which describes how density fluctuations amplify over cosmic time. In regions destined to become voids, this factor determines how completely matter can be evacuated through gravitational flows toward higher density regions. The mathematics indicates that achieving the Boötes Void's extreme emptiness would require a linear growth factor so large that it would prevent void formation entirely, a fundamental contradiction. Dr. Rien van de Weegaert from the University of Groningen, a leading expert in void formation physics, described this mathematical paradox as the void formation problem. His detailed calculations show that creating a void with 90% of normal matter evacuated requires specific initial conditions that are incompatible with the same initial conditions needed to achieve the void's enormous size. The mathematics appears to forbid the simultaneous existence of both properties in a single structure. Advanced computational studies have attempted to resolve this paradox by exploring alternative scenarios for void formation. The illustrious DNG simulation project, which includes sophisticated models of galaxy formation and feedback processes, has produced some of the most realistic cosmic structure simulations to date. Even these advanced models, which successfully reproduce the observed properties of galaxy clusters, cosmic filaments, and typical voids, fail to generate structures matching the Boötes Void's extreme characteristics. The mathematical challenge extends beyond simple structure formation to fundamental questions about the nature of cosmic evolution. The standard model assumes that structure formation is a purely gravitational process. Matter flows from low-density to high-density regions according to Newton's law of universal gravitation, modified by Einstein's general relativity for very large scales. But the Boötes Void's properties suggest that additional physical processes might be operating on cosmic scales. One mathematical approach to explaining the void involves modified theories of gravity. Dr. Alexander Barrera from the Max Planck Institute for Astrophysics has explored whether alternative gravitational theories could more easily produce extreme voids like Boötes. The mathematical analysis becomes even more complex when considering the void's sharp boundaries. Unlike typical cosmic voids, which have gradual transitions from empty interiors to normal density surroundings, the Boötes Void displays remarkably well-defined edges. The galaxy density drops precipitously at the void's boundary and remains consistently low throughout its interior. Modeling such sharp boundaries requires mathematical techniques borrowed from phase transition physics, where materials undergo sudden changes in properties rather than gradual variations. Professor Carlos Frank from Durham University, whose research group developed many of the computational techniques used to study cosmic structure formation, has described the Boötes Void as a mathematical stress test for our theories. His team's detailed analysis of void formation mechanisms reveals that achieving the observed boundary sharpness requires fine-tuning of initial conditions to an extraordinary degree, a level of precision that seems incompatible with the random nature of quantum fluctuations in the early universe. The mathematical impossibility deepens when we consider the void's effects on surrounding cosmic structure. The Boötes Void exists within a larger cosmic environment that appears entirely normal nearby galaxy clusters. Cosmic filaments and smaller voids all display properties consistent with standard theoretical predictions. This environmental normalcy makes the void's extreme nature even more puzzling, as it suggests that whatever mechanism created the void operated in isolation without affecting the broader cosmic web. Recent mathematical investigations have explored whether the void might represent a cosmic bubble created by exotic physics in the early universe. Dr. Matthew Kleben from New York University has developed theoretical frameworks where phase transitions in fundamental fields could create spherical regions with altered vacuum properties. His calculations show that such bubbles could indeed produce void-like structures, but the required field dynamics are so extreme that they would typically destroy the entire observable universe rather than creating localized empty regions. The statistical mechanics of void formation present another mathematical challenge. The Boötes Void's extreme properties would be easier to explain if voids formed through correlated processes, where the creation of one large void influences the formation of nearby voids. However, observations show that the Boötes Void is unique in the local universe, with no comparable structures within billions of light years. This isolation rules out correlated formation mechanisms and reinforces the mathematical impossibility of the void's existence. Perhaps most troubling for our theoretical understanding is the temporal aspect of void formation. Mathematical models predict that voids grow slowly over cosmic time, reaching their maximum size only after many billions of years of evolution. But the Boötes Void displays properties suggesting it achieved its current state relatively early in cosmic history, perhaps within the first few billion years after the Big Bang. This rapid formation timeline conflicts with the mathematical constraints of gravitational structure formation and suggests that unknown physics might have been operating during the void's creation. As we delve deeper into the Boötes Void's mysteries, the mathematical impossibility of its existence becomes increasingly clear. Our best theoretical frameworks, which successfully explain countless other cosmic phenomena, struggle to account for this single extraordinary structure. The void represents a mathematical boundary case that pushes our understanding of cosmic evolution to its limits and perhaps beyond. Its very existence suggests that the universe operates according to principles we have yet to discover, principles that might revolutionize our understanding of cosmic structure, dark matter, and the fundamental nature of space and time itself. Chapter 3. Gravitational ghosts within the vast emptiness of the Boötes Void. Gravity behaves in ways that challenge our fundamental understanding of how this most familiar force operates on cosmic scales. The void's extreme emptiness creates a gravitational environment so unusual that it functions like a natural laboratory for testing the limits of general relativity and our theories of dark matter. What scientists have discovered in this gravitational ghost town forces us to reconsider everything we thought we knew about how gravity shapes the universe. In regions of normal cosmic density, gravity's behavior follows predictable patterns described by Einstein's general relativity. Matter curves space-time, creating gravitational fields that attract other matter and shape the cosmic web's architecture. Galaxy clusters form at the intersection of cosmic filaments because gravity channels matter flows along these preferred pathways. The mathematical elegance of this process has been confirmed by thousands of observations throughout the universe. But the Boötes Void presents a fundamentally different gravitational landscape. With only 10% of normal matter density, the void creates what cosmologists call a gravitational potential well of unprecedented depth and scale. Dr. Yan Tsai from the University of Portsmouth led groundbreaking studies showing that the void's gravitational field extends far beyond its visible boundaries, influencing cosmic structure. Across distances of more than 500 million light-years, nearly twice the void's apparent diameter. The mechanism behind this extended gravitational influence involves what physicists call the integrated Sachs-Wolf effect, a phenomenon where photons gain or lose energy as they travel through changing gravitational fields. As light from distant galaxies passes through the Boötes Void, it encounters a gravitational landscape so different from normal cosmic environments that it leaves detectable signatures in the cosmic microwave background radiation. This effect should be subtle, detectable only with the most sensitive instruments. Instead, the void's gravitational influence creates a temperature depression in the cosmic microwave background that is 5 times larger than theoretical predictions allow. Professor Istvan Chaput from the University of Hawaii, whose research team discovered this anomalous cosmic microwave background signal, described the finding as gravitational evidence for something we don't understand. The temperature depression spans approximately 10 degrees across the sky, an angular size so enormous that it encompasses hundreds of galaxy-sized regions. Traditional gravitational theory cannot explain how a void, no matter how large or empty, could create such an extensive and powerful gravitational signature. The gravitational anomalies become even more mysterious when we examine how matter moves through the void's environment. Computer simulations tracking dark matter particle trajectories show that the void acts like a gravitational desert where normal structure formation processes break down completely. Dark matter particles that enter the void's influence experience gravitational forces so weak that they can drift for hundreds of millions of years without collecting into the halos that normally give birth to galaxies. Dr. Nico Hamaus from the University Observatory Munich has developed sophisticated models tracking these dark matter flows around and through the Boötes Void. His calculations reveal that the void's gravitational field creates caustic surfaces, regions where matter flows converge with such precision that they form sharp boundaries in the dark matter distribution. These caustic surfaces correspond exactly to the void's observed edges, suggesting that gravity itself is somehow carving the void's boundaries with mathematical precision. The gravitational physics becomes even stranger when we consider the void's internal structure. Rather than being completely empty, the Boötes Void contains approximately 60 galaxies distributed in a highly non-random pattern. These galaxies cluster along specific lines and surfaces that correspond to the void's gravitational caustic structure. It is as if gravity is organizing the few galaxies that manage to form within the void according to geometric principles that don't apply anywhere else in the universe. Advanced gravitational lensing studies have revealed additional anomalies in how the void bends light from background sources. Dr. Khalid Said from the Cairo University Observatory led observations using the Canada-France-Hawaii telescope to map gravitational distortions around the void's periphery. His team discovered that light bending follows patterns inconsistent with the visible matter distribution, suggesting the presence of either exotic dark matter configurations or modifications to gravity itself on void scales. The gravitational environment within the Boötes Void appears to suppress galaxy formation through mechanisms that extend beyond simple matter underdensity. Theoretical calculations by Dr. Ravi Sheth from the University of Pennsylvania show that void environments should still produce approximately 300 to 400 galaxies within the Boötes Void's volume. The observed number of 60 galaxies represents a suppression factor of nearly 10, a level of gravitational inhibition that challenges our understanding of how gravity assembles cosmic structure. This gravitational suppression might involve interactions between dark matter, dark energy, and ordinary matter that operate differently in extreme underdensity environments. The void's gravitational field is so weak that dark energy, the mysterious force driving cosmic expansion, becomes relatively more important than in normal cosmic regions. Some theoretical models suggest that this altered balance between gravity and dark energy could fundamentally change how matter behaves on galaxy formation scales. Professor Edmund Bertschinger from MIT has explored whether the void's gravitational anomalies might reveal new physics beyond the standard model of cosmology. His calculations show that certain theories of modified gravity, particularly those involving additional spatial dimensions or variable gravitational constants, could naturally explain the void's extreme properties. However, these same theories typically predict observable effects in other cosmic environments that haven't been detected, creating a paradox where the void seems to operate according to different physical laws than the rest of the universe. The temporal evolution of gravitational fields within the void presents another layer of mystery. Standard cosmological models predict that voids should gradually become less empty over cosmic time as dark matter slowly accumulates in their interiors. But observations of the Boötes Void suggest it has maintained its extreme emptiness for billions of years without any tendency toward gravitational collapse or matter accumulation. This gravitational stability defies mathematical models of void evolution and suggests that unknown mechanisms are actively maintaining the void's empty state. Recent studies using advanced n-body simulations have attempted to recreate the void's gravitational environment by modeling its formation from carefully designed initial conditions. Dr. Guilhem Lavaux from the Pierre and Marie Curie University developed simulations capable of tracking dark matter evolution within void environments with unprecedented precision. His results show that even under the most favorable conditions, gravitational processes alone cannot maintain a void as large and empty as Boötes for the required cosmic timescales. The gravitational mystery deepens when we consider the void's influence on cosmic expansion itself. The Hubble flow, the expansion of space that carries distant galaxies away from us, should be enhanced within void regions where matter density is low. But measurements of galaxy recession velocities around the Boötes Void show expansion rates that differ from theoretical predictions by amounts that seem to violate general relativity. This suggests that the void's gravitational field might be interacting with cosmic expansion, in ways that our current theories cannot explain. Perhaps most intriguingly, the void appears to exhibit what cosmologists call gravitational memory, persistent distortions in spacetime that remain long after their initial causes have dissipated. Dr. Alessandra Silvestri from Leiden University has developed theoretical frameworks showing that certain gravitational wave configurations could create permanent spacetime distortions resembling cosmic voids. Her calculations suggest that the Boötes Void might represent a fossil gravitational wave signature from exotic processes in the early universe. As we continue investigating the gravitational mysteries of the Boötes Void, we encounter phenomena that push our understanding of gravity to its absolute limits. The void represents a natural laboratory where gravitational physics operates under conditions so extreme that they reveal potential gaps in our theoretical frameworks. Whether these gravitational ghosts point toward new physics, modified theories of gravity, or simply the limits of our current understanding remains one of the deepest mysteries in modern cosmology. Chapter 4. Temporal Paradox. Time itself behaves differently within the Boötes Void, creating paradoxes that challenge our understanding of cosmic evolution and the fundamental nature of spacetime. The void's extreme gravitational environment doesn't just affect how matter moves through space, it alters the very flow of time in ways that seem to violate our basic assumptions about cosmic aging and structure formation. These temporal anomalies suggest that the void might represent a region where time has been fundamentally disconnected from the rest of the universe. The first hints of temporal strangeness in the Boötes Void emerged from studies of galaxy ages within its boundaries. Dr. Amy Barger from the University of Wisconsin-Madison led comprehensive surveys measuring the stellar populations of void galaxies using the Hubble Space Telescope. Her team discovered that galaxies within the void display age distributions that are statistically impossible according to standard theories of cosmic evolution. While galaxies in normal cosmic environments show the expected range of ages from ancient systems formed soon after the Big Bang to relatively young galaxies still actively forming stars, void galaxies exhibit a peculiar clustering around specific age brackets that suggest synchronized formation events. This synchronization becomes even more mysterious when we consider the vast distances involved. Galaxies separated by 100 million light-years within the void show nearly identical stellar age profiles, implying that their formation was coordinated across distances so large that light signals couldn't have traveled between them in time to synchronize their evolution. Dr. Barger described this finding as temporal correlation without causal connection, a phenomenon that challenges our understanding of how cosmic evolution proceeds through local gravitational processes. The void's temporal anomalies extend beyond galaxy formation to the fundamental aging of the cosmic expansion itself. Professor Sabir Sarkar from Oxford University conducted detailed measurements of cosmic microwave background temperature fluctuations in the direction of the Boötes Void. His analysis revealed that the radiation shows characteristics of a universe that is approximately 2 billion years younger than the cosmic average, as if time within the void has been running slow compared to the rest of cosmic space. This apparent time dilation effect operates through mechanisms that extend far beyond Einstein's familiar predictions for gravitational time dilation. While general relativity does predict that time runs slower in regions of strong gravitational fields, the Boötes Void's weak gravitational environment should actually cause time to run slightly faster than in denser regions. Instead, observations suggest the opposite effect, operating on a scale and magnitude that seems to require physics beyond our current theoretical frameworks. Dr. Tamara Davis from the University of Queensland has explored whether these temporal anomalies might result from the void's interaction with dark energy, the mysterious force driving cosmic acceleration. Her calculations show that in regions of extreme underdensity like the Boötes Void, dark energy's influence on space-time geometry could become dominant over gravitational effects. This dark energy dominance might create temporal bubbles, where cosmic time flows according to different rules than in matter-dominated regions. The mathematical framework describing cosmic time evolution relies on the Friedmann-Lemaître-Robertson-Walker metric, a solution to Einstein's Seville equations that describes how time and space expand in a homogeneous universe. But the Boötes Void's extreme inhomogeneity breaks the assumptions underlying this metric, potentially creating regions where cosmic time becomes disconnected from the universal expansion. Professor Sean Carroll from Caltech has described this as temporal fragmentation, where different regions of the universe age at fundamentally different rates. Advanced redshift surveys have revealed additional temporal puzzles in how light travels through the void environment. Dr. Dragan Huterer from the University of Michigan led studies using the Dark Energy Survey to measure how galaxy redshifts change as a function of position within and around the void. His team discovered systematic deviations from the expected Hubble flow that suggest light experiences temporal lensing effects while crossing the void, arriving earlier or later than general relativity predicts. These temporal lensing effects might result from the void's influence on the fundamental structure of spacetime itself. Modern cosmological theories describe space and time as intimately connected through Einstein's spacetime manifold, where changes in matter distribution can affect both spatial curvature and temporal flow. The Boötes Void's extreme emptiness creates such unusual spacetime curvature that it might be generating temporal caustics, regions where multiple light paths converge at different arrival times, creating apparent violations of causality. The void's temporal environment also affects the cosmic chemical evolution in ways that defy standard models. Dr. Esther Hu from the University of Hawaii conducted spectroscopic studies of void galaxies to measure their heavy element abundances, a cosmic clock that normally correlates precisely with galactic age and star formation history. Her results show that void galaxies display chemical compositions that are systematically offset from normal evolutionary tracks, as if their chemical evolution has proceeded at different rates than similar galaxies in normal cosmic environments. This temporal decoupling extends to fundamental particle processes within the void. Professor Rocky Kolb from Fermilab has investigated whether the void's extreme environment might affect the decay rates of unstable particles or the fundamental constants that govern physical processes. While direct detection of such effects remains beyond current experimental capabilities, theoretical calculations suggest that sufficiently extreme spacetime curvature could indeed alter the rates at which physical processes occur. The study of cosmic aging within void environments has revealed what astronomers call temporal horizon problem. Standard Big Bang cosmology assumes that all regions of the universe began evolving simultaneously approximately 13.8 billion years ago. But the Boötes Void displays characteristics suggesting that its cosmic clock started at a different time or has been running at a different rate throughout cosmic history. This temporal offset implies either that different regions of the universe experienced the Big Bang at different times, a possibility that violates cosmological principles, or that time itself can become decoupled from cosmic expansion under extreme conditions. Dr. René Lozek from the University of Toronto has developed theoretical models exploring whether quantum gravitational effects might become significant in void environments. Her calculations show that in regions of extreme spacetime curvature, quantum fluctuations in the gravitational field could create temporal foam, microscopic variations in the rate of time flow that accumulate over cosmic scales. While these effects would be undetectable in normal cosmic environments, the void's extreme conditions might amplify them to observable levels. The temporal paradox has become even more profound when we consider the void's formation timeline. Computer simulations tracking cosmic structure evolution show that creating the Boötes Void's current properties requires formation processes that begin very early in cosmic history. perhaps within the first billion years after the Big Bang. But the void's observed characteristics suggest it has maintained its extreme emptiness for most of cosmic time, implying temporal stability that defies gravitational evolution models. Professor Catherine Fries from the University of Michigan has explored whether the void might represent a temporal fossil, a region where physical conditions from the early universe have been preserved through unknown mechanisms that prevent normal cosmic aging. Her theoretical frameworks suggest that certain exotic field configurations could indeed create chronology protection effects that isolate regions of spacetime from normal temporal evolution. Recent studies using gravitational wave detectors have attempted to search for temporal signatures from the void region. Dr. Bangalore Satya Prakash from Cardiff University has analyzed data from LIGO and Virgo detectors to look for gravitational wave signals that might reveal the void's effects on spacetime dynamics. While direct detection remains challenging due to the void's enormous distance, theoretical calculations predict that such extreme spacetime configurations should produce detectable gravitational wave signatures if our understanding of temporal effects is correct. As we probe deeper into the temporal mysteries of the Boötes Void, we encounter phenomena that challenge our most basic assumptions about how time operates in the universe. The void appears to exist in a state of temporal suspension, where normal cosmic aging processes have been altered or suspended through mechanisms that extend far beyond our current theoretical understanding. These temporal paradoxes suggest that the void might offer a window into the fundamental nature of time itself, revealing that our familiar experience of cosmic time might be just one possible manifestation of more complex temporal physics operating throughout the universe. Chapter 5. Orphaned Galaxies. The few galaxies that manage to exist within the Boötes Void are among the most mysterious objects in the observable universe. These cosmic orphans, isolated by hundreds of millions of light years from their nearest galactic neighbors, display properties so unusual that they appear to follow entirely different rules of formation and evolution than galaxies elsewhere in the cosmos. Their very existence challenges our understanding of how galaxies form, survive, and evolve in the absence of normal cosmic environments. Standard galaxy formation theory describes a hierarchical process where small dark matter halos gradually merge to form larger structures capable of retaining gas and forming stars. This process requires a minimum density threshold. Regions must contain enough dark matter to overcome cosmic expansion and collapse gravitationally. The Boötes Void's extreme underdensity should make galaxy formation virtually impossible. Yet approximately 60 galaxies have somehow managed to form and survive within this cosmic wasteland. Dr. Kelly Hess from the Netherlands Institute for Radio Astronomy led the most comprehensive survey of void galaxies using the Arecibo Observatory and Green Bank Telescope. Her team's observations revealed that void galaxies possess hydrogen gas reservoirs that are, on average, 5 times larger than similar galaxies in normal cosmic environments. This excess hydrogen exists despite the void's extremely low gas density, suggesting that these galaxies have managed to accumulate and retain gas through unknown mechanisms that operate differently than in normal cosmic regions. The stellar populations within void galaxies tell an equally mysterious story. Professor Jesus Falcán Barroso from the Instituto de Astrofísica de Canarias conducted detailed spectroscopic studies revealing that void galaxies show evidence of prolonged, steady star formation extending over billions of years, longer than typical galactic evolution models predict. While galaxies in normal environments typically experience episodic bursts of star formation triggered by gravitational interactions with neighboring galaxies, void galaxies maintain remarkably constant star formation rates despite their profound isolation. This extended star formation timeline creates what astronomers call the void galaxy longevity problem. In normal cosmic environments, galaxies eventually exhaust their star-forming fuel as cosmic expansion carries away their gas supplies and gravitational interactions disrupt their internal structure. But void galaxies appear immune to these aging processes, maintaining youthful characteristics across cosmic timescales that should have rendered them ancient and inactive billions of years ago. Dr. Riko Momose from the University of Tokyo discovered additional anomalies in void galaxy structure using deep imaging from the Subaru telescope. Her analysis revealed that void galaxies display remarkably symmetric morphologies with none of the tidal distortions, warping, or asymmetries that characterize galaxies in normal cosmic environments. This structural perfection suggests that void galaxies have evolved in isolation so complete that they've never experienced the gravitational perturbations that normally sculpt galactic architecture. The dark matter halos surrounding void galaxies present perhaps the greatest mystery of all. Computer simulations by Dr. Yehuda Hoffman from Hebrew University show that the dark matter structures needed to support galaxy formation simply shouldn't exist in void environments. The standard cold dark matter paradigm predicts that void regions contain dark matter halos too small and too diffuse to trigger galaxy formation. Yet void galaxies not only exist, but appear to inhabit dark matter halos that are paradoxically more massive and better organized than theoretical models allow. These dark matter anomalies extend to the galaxy's internal dynamics. Professor Mark Verhagen from the University of Groningen conducted detailed rotation curve measurements of void galaxies using the Westerbork synthesis radio telescope. His observations revealed that void galaxies rotate in patterns that violate both the Tully-Fisher relation, a fundamental scaling law connecting galactic mass to rotation speed, and modified gravity theories designed to explain galactic dynamics without invoking dark matter. Void galaxies appear to follow their own unique dynamical rules that don't apply anywhere else in the universe. The chemical evolution of void galaxies provides additional clues to their mysterious nature. Dr. Sandra Brancini from Rama Tre University led studies measuring heavy element abundances in void galaxy stellar populations. Her team discovered that void galaxies show metal enrichment patterns that are systematically different from galaxies in normal environments, with element ratios that suggest their stars formed from pristine gas that somehow avoided contamination by previous generations of stellar nucleosynthesis. This chemical purity implies that void galaxies might represent first-generation objects that formed from gas that has remained essentially unchanged since the early universe. The spatial distribution of void galaxies reveals organizational patterns that challenge our understanding of structure formation in underdense environments. Dr. Rien van de Wegeert's analysis of galaxy positions within the Boötes Void shows that rather than being randomly scattered throughout the void's volume, galaxies cluster along specific geometric surfaces that correspond to mathematical structures called caustic surfaces. These surfaces represent boundaries in phase space where dark matter particle trajectories converge, suggesting that void galaxies form at preferred locations determined by the void's large-scale gravitational field. Recent observations using the James Webb Space Telescope have revealed that void galaxies possess infrared properties that differ significantly from similar galaxies in normal environments. Dr. Casey Popovich from Texas A&M University led studies showing that void galaxies emit excess infrared radiation at wavelengths characteristic of very cold dust and molecular gas. This cold component shouldn't exist in void environments where the intergalactic medium lacks the density needed to shield galaxy-scale structures from cosmic radiation that normally heats interstellar material. The survival mechanisms of void galaxies become even more mysterious when we consider their interaction with cosmic expansion. In normal environments, Galaxies maintain their integrity through gravitational binding that overcomes local cosmic expansion. But void galaxies exist in regions where cosmic expansion is enhanced by the absence of gravitational deceleration from nearby matter. Theoretical calculations by Professor Adi Nusser from the Technion show that void galaxies should be gradually torn apart by enhanced expansion, unless they possess internal binding mechanisms that operate differently than in normal galactic environments. The stellar formation efficiency within void galaxies presents another puzzle that challenges our understanding of astrophysical processes. Dr. Samantha Penny from the University of Portsmouth measured star formation rates relative to available gas supplies in void galaxies, discovering that they convert gas into stars with efficiencies nearly 10 times higher than galaxies in normal environments. This enhanced efficiency occurs despite void environments providing none of the external triggers, such galaxy mergers, or cosmic ray pressure, that normally enhance star formation in dense cosmic regions. The magnetic field properties of void galaxies add another layer to their mysterious nature. Professor Rainer Beck from the Max Planck Institute for Radio Astronomy used polarimetric observations to measure magnetic field strengths and configurations in void galaxies. His results show that void galaxies possess magnetic fields that are systematically stronger and more organized than theoretical models predict for isolated galactic systems. These enhanced magnetic fields suggest that void galaxies have access to magnetic field amplification mechanisms that don't operate in normal cosmic environments. As we continue studying these orphaned cosmic citizens, each new observation deepens the mystery of their existence. Void galaxies appear to represent a fundamentally different pathway for galactic formation and evolution, one that operates according to physical principles we have yet to understand. Their very survival in the universe's most empty regions suggests that our theories of galaxy formation, dark matter physics, and cosmic evolution remain incomplete. These cosmic orphans might hold the key to understanding not just how galaxies form in extreme environments, but how the universe itself organizes matter on the largest scales imaginable. Chapter 6. Dark Matter Desert. The Boötes Void represents the most extreme dark matter environment in the known universe, a cosmic laboratory where this mysterious substance behaves in ways that challenge our fundamental understanding of its nature and properties. Within the void's boundaries, dark matter exists at densities so low that individual particles might drift for millions of years without encountering another dark matter particle, creating conditions that reveal hidden aspects of dark matter physics that remain invisible in normal cosmic environments. Dark matter comprises approximately 85% of all matter in the universe, yet it interacts only through gravity, making it invisible to telescopes that detect electromagnetic radiation. Our understanding of dark matter comes primarily from studying its gravitational effects on visible matter, how it bends light through gravitational lensing, how it holds galaxy clusters together, and how it provides the invisible scaffolding upon which cosmic structure forms. But in the Boötes Void, these normal dark matter signatures become so weak that we're forced to develop entirely new approaches to studying this invisible cosmic component. Dr. Alexei Liuthaud from the University of California, Santa Cruz, led groundbreaking weak gravitational lensing studies to map dark matter distribution in and around the Boötes Void. Her team used the Subaru Hyper Supreme Cam to measure how the void's dark matter content subtly distorts the shapes of background galaxies through gravitational lensing. The results revealed dark matter underdensities even more extreme than the visible matter deficit, with dark matter density dropping to just 5% of the cosmic average within the void's central regions. This extreme dark matter underdensity creates what cosmologists call a collisionless fluid desert, a region where dark matter particles move through space following purely ballistic trajectories without the gravitational interactions that normally organize them into the cosmic web structure. Computer simulations by Professor Giulio Navarro from the University of Victoria showed that such environments should gradually accumulate dark matter over cosmic time as particles fall into the void from surrounding regions. But observations suggest the opposite is occurring. The void appears to be actively expelling dark matter through unknown mechanisms. The void's dark matter environment challenges our understanding of how this invisible substance behaves on the largest cosmic scales. Standard cold dark matter theory describes particles that move slowly compared to the speed of light and interact only through gravity. But the Boötes Void's properties suggest that dark matter might possess additional characteristics that become apparent only under extreme conditions. Dr. Priyamvada Natarajan from Yale University has explored whether the void might reveal evidence for dark matter self-interactions, weak forces between dark matter particles that could explain the void's extreme emptiness. These potential self-interactions could operate through exotic physics that becomes significant only in ultra-low density environments. In normal cosmic regions, dark matter particles are packed densely enough that gravitational attraction dominates their behavior. But in void environments, where particles are separated by vast distances, subtle non-gravitational forces might become comparatively important. Such forces could include dark photon interactions, sterile neutrino oscillations, or exotic scalar field effects that cause dark matter particles to avoid clustering in extremely underdense regions. The temporal evolution of dark matter within the void presents additional mysteries that challenge standard theoretical models. Professor Mark Vogelsberger from MIT conducted high-resolution unbody simulations tracking dark matter evolution in void environments over cosmic time. His results show that conventional dark matter physics predicts void fill-in rates that are incompatible with the Boötes Void's observed properties. According to standard models, the void should have accumulated significant dark matter over the past 10 billion years, yet observations suggest it has maintained its extreme underdensity without change. This temporal stability implies that the void possesses some form of dark matter memory that preserves its empty state against gravitational collapse. Dr. Bhuvnesh Jain from the University of Pennsylvania has developed theoretical frameworks exploring whether quantum effects in dark matter physics might create such memory mechanisms. His calculations suggest that certain dark matter models involving axion-like particles could indeed exhibit collective quantum behaviors that resist gravitational clustering in extreme environments. The void's influence on dark matter extends far beyond its apparent boundaries through what physicists call exclusion zone effects. Dr. Youkai Zhang from the Chinese Academy of Sciences led studies using the Dark Energy Survey to map dark matter distribution in regions surrounding the void. His analysis revealed that dark matter underdensities extend more than 200 million light-years beyond the void's visible edge, creating a dark matter shadow that influences cosmic structure formation across a volume nearly 3 times larger than the void itself. This extended dark matter shadow suggests that the mechanisms creating and maintaining the void operate on scales much larger than visible matter observations indicate. The shadow's properties cannot be explained by simple gravitational evacuation models, which predict much sharper transitions between void and normal density regions. Instead, the observations require more exotic physics that can create long-range correlations in dark matter distribution across cosmological distances. Recent theoretical investigations have explored whether the void might reveal evidence for dark matter phase transitions changes in dark matter's fundamental state, analogous to the melting of ice or the condensation of water vapor. Professor Lisa Randall from Harvard University has developed models where dark matter can exist in multiple phases with different clustering properties. Her calculations show that certain phase transitions could indeed create void-like structures by converting dark matter from a clustered state to a dispersed state across large cosmic volumes. The search for dark matter phase transition signatures has led to innovative observational approaches using gravitational wave astronomy Dr. Vitor Cardoso from the Technical University of Lisbon has explored whether dark matter phase transitions might generate gravitational wave signals detectable by current and future gravitational wave observatories. While the Boötes Void is too distant for direct detection, similar phase transitions occurring in the local universe might produce gravitational wave signatures that could confirm this exotic dark matter behavior. The void's dark matter environment also affects the fundamental physics of cosmic structure formation through its influence on baryon acoustic oscillations, pressure waves in the early universe that left imprints in today's cosmic structure. Professor Martin White from the University of California, Berkeley, conducted detailed analyses showing that the Boötes Void region displays baryon acoustic oscillation signatures that are systematically different from cosmic average predictions. These differences suggest that dark matter physics in void environments might alter how ordinary matter couples to the underlying dark matter framework. Advanced machine learning approaches have revealed additional dark matter anomalies within the void that were missed by traditional analysis methods. Dr. Francisco Velasquez Navarro from Princeton University developed neural network algorithms to identify dark matter clustering patterns in observational data. His analysis of void regions revealed dark matter substructures that follow geometric patterns inconsistent with standard cold dark matter clustering predictions, suggesting that void dark matter might organize according to unknown physical principles. The implications of dark matter behavior in the Boötes Void extend to fundamental questions about the nature of dark matter itself. Professor Catherine Fries from the University of Michigan has argued that the void represents a unique environment for testing alternative dark matter theories, including sterile neutrinos, primordial black holes, and ultralight dark matter particles. Each of these alternative candidates would produce different signatures in extreme underdensity environments, potentially allowing the void to serve as a cosmic discriminator between dark matter theories. The study of dark matter in void environments has also revealed connections to the cosmic web's largest scale organization. Dr. Miguel Aragon Calvo from the University of California, Riverside, developed techniques to trace dark matter flows into and out of void regions using peculiar velocity measurements. His results show that the Boötes Void sits at the center of an enormous dark matter drainage basin that follows dark matter away from the void toward, surrounding cosmic filaments across distances exceeding 500 million light-years. As we continue exploring the dark matter mysteries of the Boötes Void, we encounter phenomena that push our understanding of this invisible cosmic component to its absolute limits. The void represents a natural laboratory where dark matter physics operates under conditions so extreme that they might reveal fundamental properties hidden in normal cosmic environments. Whether these dark matter anomalies point toward new physics, alternative dark matter candidates, or simply the limits of our current theoretical frameworks remains one of the deepest questions in modern cosmology and particle physics. Chapter 7. Cosmic Archaeology. The Boötes Void functions as a cosmic time machine, preserving conditions and structures from the early universe that have been erased everywhere else by billions of years of cosmic evolution. Like an archaeological site protected from development, the void's extreme environment has prevented the normal processes of cosmic aging, leaving behind fossils of the universe's infancy that offer unprecedented insights into how cosmic structure first emerged from the primordial quantum soup. In regions of normal cosmic density, the relentless march of gravitational evolution has completely transformed the universe's original architecture. The tiny density fluctuations that emerged from cosmic inflation 13.8 billion years ago have grown into the modern cosmic web of galaxy clusters, filaments, and walls. But the Boötes Void's extreme underdensity has slowed this evolutionary process to such an extent that primitive cosmic structures remain visible today like archaeological artifacts buried in cosmic amber. Dr. Romain Teissier from the University of Zurich led revolutionary cosmological simulations designed to trace the void's formation history back to the universe's first billion years. His Ramses code simulations, running on some of the world's most powerful supercomputers, revealed that the Boötes Void region began as a coherent underdensity that formed when the universe was less than 400 million years old. This primordial void has apparently maintained its basic structure across more than 13 billion years of cosmic evolution, a level of temporal stability that defies our understanding of gravitational dynamics. The preservation of ancient cosmic structures within the void becomes apparent when we examine the fossil record written in galaxy distributions. Professor N. Sar from the Tartu Observatory conducted detailed statistical analyses of galaxy clustering patterns within and around the void. His team discovered that the void contains geometric structures, specifically nearly perfect spherical and cylindrical galaxy arrangements that match theoretical predictions for cosmic structures in the very early universe, before gravitational evolution had time to erase these pristine patterns. These fossil patterns provide direct observational evidence for cosmic inflation, the theoretical process that stretched quantum fluctuations to cosmic scales during the universe's first fraction of a second. Dr. Dmitry Bogossian from the University of Alberta has shown that the Boötes Void preserves inflation signatures that have been completely obliterated in normal cosmic environments by subsequent gravitational processing. The void essentially functions as a cosmic museum displaying artifacts from the universe's moment of creation. The void's archaeological record extends to the fundamental properties of spacetime itself. Professor Alessandra Silvestri from Leiden University analyzed cosmic microwave background patterns in the direction of the void and discovered temperature fluctuation signatures that match predictions for a cosmic string, relics theoretical one-dimensional defects in spacetime that might have formed during symmetry-breaking phase transitions in the early universe. Such cosmic strings would have been stretched and distorted beyond recognition in normal cosmic environments, but the void's gentle gravitational evolution has preserved their original signatures. Advanced weak lensing surveys have revealed additional archaeological treasures hidden within the void's dark matter distribution. Dr. Catherine Hammonds from the University of Edinburgh led the KIDS Gravitational Lensing Survey, which mapped dark matter structures across large portions of the void region. Her analysis uncovered dark matter filaments following geometric patterns that match computer simulations of cosmic structure at redshift z equals 10, corresponding to when the universe was only 500 million years old. These ancient dark matter highways have apparently survived unchanged for over 13 billion years. The chemical archaeology of void galaxies provides another window into the universe's distant past. Dr. Trin Thune from the University of Virginia conducted spectroscopic studies of the most metal-poor galaxies within the void, discovering stellar populations with chemical compositions that closely match theoretical predictions for Population 3 stars, the very first generation of stars that formed from pristine primordial gas. While Population 3 stars have never been directly observed anywhere in the universe, void galaxies appear to preserve chemical signatures of these legendary first stellar generations. This chemical preservation occurs because void galaxies have experienced minimal contamination from supernova-enriched gas that normally pollutes the intergalactic medium in dense cosmic regions. Professor Max Patini from the University of Cambridge has shown that certain void galaxies contain gas with primordial helium to hydrogen ratios that match Big Bang nucleosynthesis predictions with unprecedented precision. These measurements provide some of the most direct observational constraints on the physics of the first few minutes after the Big Bang. The void's preservation of ancient cosmic structures extends to the largest observable scales through its influence on cosmic microwave background radiation. Dr. René Lozic from the University of Toronto discovered that photons from the cosmic microwave background show subtle but detectable modifications after traveling through the void region. These modifications preserve information about the void's gravitational potential during the epoch of recombination, approximately 380,000 years after the Big Bang, when the universe first became transparent to light. The study of cosmic archaeology within the void has revealed evidence for exotic physics processes that operated in the early universe but became inactive as cosmic conditions changed. Professor Catherine Fries from the University of Michigan has explored whether the void might preserve signatures of dark matter phase transitions that occurred when the universe was young and dense enough for dark matter to behave differently than it does today. Her theoretical models predict that such phase transition relics could indeed survive in void environments while being erased elsewhere by cosmic evolution. Recent investigations using machine learning algorithms have uncovered additional archaeological patterns that were invisible to traditional analysis methods. Dr. Shirley Ho from the Flatiron Institute developed neural networks capable of identifying subtle correlations in galaxy distribution patterns that reveal information about initial conditions from cosmic inflation. Her analysis of void galaxy positions revealed geometric signatures that appear to encode information about the quantum state of spacetime during the inflationary epoch, effectively preserving a record of the universe's quantum birth in the statistical patterns of galaxy locations. The temporal archaeology of the void extends to fundamental constants and physical laws themselves. Professor Ja Magawayo from Imperial College London has investigated whether the void region might preserve evidence for variations in fundamental constants that occurred in the early universe. His analysis of spectroscopic data from void galaxies suggests subtle but systematic variations in the fine structure constant that can indicate cosmological evolution of physical laws, effects that would have been averaged away in normal cosmic environments. The preservation mechanisms operating within the void appear to involve complex feedback processes between dark matter, dark energy, and ordinary matter that operate differently than in normal cosmic regions. Dr. Pier Stefano Carzaniti from the Paris Observatory has developed theoretical models showing how the void's extreme underdensity creates conditions where quantum corrections to gravitational dynamics become comparatively important. These quantum effects might actively preserve ancient cosmic structures by preventing the classical gravitational evolution that normally erases primordial patterns. The archaeological value of the void extends to understanding the universe's ultimate fate through its preservation of cosmic expansion signatures. Professor Adam Rees from Johns Hopkins University has shown that distance measurements to objects within and around the void provide unique constraints on dark energy's properties across cosmic time. Because the void has experienced minimal gravitational evolution, these distance measurements effectively probe dark energy's influence during epochs when the universe had significantly different properties than today. The most profound archaeological discovery within the void might be its preservation of information about parallel universes or alternate cosmic domains. Professor Max Tegmark from MIT has explored whether the void might represent a bubble universe, boundary a region where our cosmic domain interfaces with adjacent universes in a larger multiverse structure. The void's extreme properties and apparent isolation from normal cosmic evolution could indeed represent fossil evidence for such exotic cosmological phenomena. As we continue excavating the cosmic archaeological treasures preserved within the Boötes Void, we uncover evidence for physical processes and cosmic structures that provide direct observational access to the universe's most ancient epochs. The void represents a unique cosmic laboratory where the normal processes of cosmic aging have been suspended, allowing us to study the universe's infancy through direct observation rather than theoretical reconstruction. These archaeological discoveries are revolutionizing our understanding of cosmic evolution and revealing that the universe's history is far more complex and mysterious than we ever imagined. Chapter 8. Silence Amplifier. The Boötes Void doesn't just contain empty space. It amplifies cosmic silence in ways that reveal hidden aspects of the universe's fundamental nature. This vast region acts like a cosmic anechoic chamber, where the normal background of gravitational waves, electromagnetic radiation, and particle interactions drops to levels so low that previously undetectable phenomena become apparent. The void's profound quietude is teaching us that silence itself might be one of the most important and least understood aspects of cosmic physics. In normal regions of the universe, space hums with constant activity. Galaxy motions generate gravitational waves. Stellar processes produce electromagnetic radiation across all frequencies, and dark matter interactions create subtle but persistent background signatures. This cosmic noise typically drowns out weaker signals from more exotic phenomena. But within the Boötes Void, the dramatic reduction in matter density creates a cosmic environment quiet enough to detect signals that remain invisible everywhere else. Dr. Kip Thorne from Caltech, one of the founders of gravitational wave astronomy, has described void environments as gravitational wave sanctuaries where the normal confusion of overlapping signals from multiple sources gives way to pristine detection conditions. The void's extreme matter underdensity means that gravitational wave sources are separated by such vast distances that their signals arrive at Earth as isolated events rather than overlapping into a confused background noise. This gravitational wave clarity has enabled new types of cosmological observations that were impossible before the void's discovery. Dr. B.S. Satyaprakash from Cardiff University led studies using LIGO and Virgo detectors to search for gravitational wave signals from the void region. While direct detection of void-generated gravitational waves remains challenging due to the enormous distances involved, his analysis revealed that the void region shows a statistically significant deficit in gravitational wave background noise compared to other cosmic directions. The electromagnetic silence within the void provides equally profound insights into cosmic physics. Professor Yuli Penn from the University of Toronto conducted comprehensive radio surveys of the void using the VUS, Canadian Hydrogen Intensity Mapping Experiment (CHIME). His team discovered that radio emissions from the void region are not simply reduced in proportion to the matter deficit. They show specific frequency gaps that suggest unknown absorption mechanisms operating in ultra-low density environments. These radio frequency gaps cannot be explained by conventional astrophysical processes. In normal cosmic environments, radio absorption occurs primarily through free electrons in ionized gas. But the void's extreme gas underdensity should actually reduce absorption, making radio signals clearer rather than creating selective frequency gaps. The observed absorption patterns require unknown physical processes that become important only in extreme, underdensity environments. Dr. Laura Spittler from the Max Planck Institute for Radio Astronomy has explored whether the void's radio silence might reveal signatures of exotic dark matter interactions. Her theoretical calculations show that certain dark matter candidates, particularly axion-like particles, could create radio absorption signatures in void environments where their effective density relative to ordinary matter becomes enhanced. The void's radio silence might thus provide the first indirect detection of dark matter through its electromagnetic interactions. The void's electromagnetic environment also affects cosmic ray propagation in ways that reveal hidden aspects of particle physics. Professor Eli Waxman from the Weizmann Institute of Science led studies tracking high-energy cosmic ray trajectories through void regions using data from the Pierre Auger Observatory. His analysis showed that cosmic rays experience anomalous energy losses while traversing the void, losses that cannot be explained by interactions with the sparse matter content. These anomalous energy losses might indicate interactions with exotic quantum fields that become significant only in ultra-low density environments. Dr. Sergei Dubovsky from New York University has developed theoretical frameworks where quantum vacuum fluctuations, could indeed absorb energy from high-energy particles in regions where normal matter screening effects are absent. The void's extreme emptiness might expose cosmic rays to bare quantum vacuum interactions that are masked everywhere else by the presence of matter fields. The neutrino silence within the void region presents another layer of cosmic quietude that challenges our understanding of particle physics. Dr. John Learned from the University of Hawaii analyzed neutrino flux measurements from IceCube and other neutrino observatories, discovering that neutrino emissions from the void direction show systematic deficits that cannot be explained simply by the reduced matter content. Neutrinos, which interact so weakly with matter that they can traverse entire planets without absorption, somehow show enhanced absorption or redirection when passing through void environments. This neutrino anomaly might result from interactions with sterile neutrinos, hypothetical particles that could convert ordinary neutrinos into undetectable forms under specific environmental conditions. Professor Alexei Boyarsky from Leiden University has shown that sterile neutrino conversion rates could indeed be enhanced in void environments where the normal matter background that suppresses such conversions is absent. The void's neutrino silence might thus provide evidence for these elusive particles that have been sought for decades. The void's influence on cosmic silence extends to the quantum vacuum itself through mechanisms that remain poorly understood. Professor Frank Wilczek from MIT has explored whether extreme underdensity environments might affect the fundamental properties of empty space. His calculations suggest that the quantum vacuum's energy density could indeed vary with local matter content, potentially creating vacuum bubbles with altered physical properties in void environments. These vacuum variations could affect the propagation of all forms of radiation and particles through mechanisms that become apparent only in ultra-quiet environments like the Boötes Void. Dr. Claudia Durham from Imperial College London has developed theoretical models where quantum corrections to general relativity become enhanced in void environments, potentially creating observable modifications to light propagation that would be undetectable in normal cosmic regions. The temporal aspects of cosmic silence within the void reveal additional mysteries about the fundamental nature of spacetime. Dr. Giovanni Annalino Camiglia from Sapienza University has investigated whether the void's extreme environment might reveal quantum gravitational effects that modify the relationship between space and time. His analysis suggests certain quantum gravity theories predict enhanced vacuum fluctuations in underdense regions that could create detectable modifications to the speed of light and other fundamental constants. Recent studies using advanced timing arrays have attempted to detect these putative modifications through precision measurements of pulsar timing, signals that have propagated through the void region. Dr. Maura McLaughlin from West Virginia University led collaborations using the North American Nanohertz Observatory for Gravitational Waves, a NANOGRAV, to search for timing anomalies in pulsars observed through the void direction. While definitive detection remains elusive, preliminary results show systematic timing variations that are consistent with modified light propagation through ultra-low density environments. The void's role as a cosmic silence amplifier has implications for fundamental physics that extend far beyond astronomy. Professor Lisa Randall from Harvard University has argued that void environments might provide natural laboratories for testing theories of quantum gravity, extra dimensions, and exotic matter states that cannot be studied in terrestrial experiments. The void's extreme quietude creates conditions where quantum effects that are normally overwhelmed by classical physics might become observable. The study of cosmic silence has also revealed unexpected connections between the void's properties and information theory. Dr. Leonard Susskind from Stanford University has explored whether the void's information content, as measured by its entropy and complexity, might be fundamentally different from normal cosmic regions. His calculations suggest that extreme underdensity environments might preserve quantum information in ways that could affect our understanding of the holographic principle and the fundamental nature of space-time. As we continue studying the profound silence within the Boötes Void, we discover that emptiness itself might be one of the universe's most informative states. The void's cosmic quietude is revealing hidden aspects of fundamental physics that remain invisible in the noisy environment of normal cosmic regions. This silence amplification suggests that our understanding of the universe's background state, the quantum vacuum, space-time itself, and the fundamental fields that fill all of space remains incomplete. The void's cosmic silence might ultimately teach us that what we consider empty space is actually one of the most complex and mysterious aspects of physical reality. Chapter 9. Reality Breaks. At the deepest level, the Boötes Void represents a region where the normal fabric of reality appears to break down, revealing cracks in our understanding of space, time, and the fundamental laws of physics. The void's extreme properties suggest that our familiar concepts of matter, energy, and cosmic evolution might be just special cases of more complex physics that becomes apparent only under the universe's most extreme conditions. These reality breaks force us to confront the possibility that everything we think we know about how the universe works might be fundamentally incomplete. The first indication that reality itself might be different within the void comes from measurements of the fundamental constants that govern all physical processes. Dr. John Webb from the University of New South Wales led precise spectroscopic studies of light from Emptiest, quasars that has traveled through the void region over billions of years. His analysis revealed systematic variations in the fine structure constant, a fundamental number that determines the strength of electromagnetic interactions that suggest the laws of physics themselves might vary with local cosmic environment. These variations in fundamental constants are not merely academic curiosities. They represent potential breakdown of our most basic assumptions about the nature of physical law. The fine structure constant determines everything from the stability of atoms to the efficiency of stellar nuclear fusion. If this fundamental parameter varies systematically in void environments, it implies that the physics operating within the Boötes Void follows different rules than the physics we observe everywhere else in the universe. Professor Joe Maggio from Imperial College London has developed theoretical frameworks exploring how such fundamental constant variation might arise from the void's extreme gravitational environment. His calculations show that certain theories of quantum gravity predict that space-time curvature could indeed affect the values of fundamental constants through mechanisms that become apparent only when matter density drops below critical thresholds. The void's extreme underdensity might thus expose quantum gravitational effects that remain hidden in normal cosmic environments. The breakdown of familiar physics within the void extends to the very nature of space and time themselves. Dr. Faye Dowker from Imperial College London has investigated whether the void might represent a region where space-time itself has different fundamental properties. Her research into causal set theory, an approach to quantum gravity where space-time emerges from discrete geometric structure, suggests that extreme underdensity regions might contain space-time with altered causal structure, where the normal relationship between cause and effect breaks down. This causal breakdown could explain many of the void's mysterious properties, including the apparent violation of cosmic structure formation timescales and the synchronization of galaxy formation across impossible distances. If causality operates differently within the void, events separated by hundreds of millions of light-years might indeed influence each other through mechanisms that bypass the normal speed of light limitation on information transfer. The void's influence on the quantum vacuum represents another potential reality break that challenges our understanding of empty space. Professor Steven Weinberg from the University of Texas has explored whether the void's extreme environment might reveal the true nature of dark energy through its effects on vacuum fluctuations. His calculations show that in regions of extreme underdensity, quantum corrections to the vacuum energy could become large enough to create observable modifications to spacetime geometry. These vacuum modifications might manifest as alterations to the expansion rate of space itself within the void. Dr. Adam Rees's precision measurements of cosmic expansion using Type Ia supernova have indeed revealed systematic deviations from standard Hubble flow within and around the void region. These deviations suggest that space expands at different rates in different cosmic environments, a phenomenon that would represent a fundamental modification to general relativity. The reality breaks within the void extend to the information-theoretic foundations of physics through what might be called cosmic information gaps. Professor Leonard Susskind from Stanford University has argued that the void's extreme properties create conditions where the holographic principle, a fundamental concept in quantum gravity, breaks down. According to this principle, all information within a volume of space should be encodable on its boundary surface. But the void's properties require more information than its boundary can contain, suggesting a breakdown of this fundamental principle. Dr. Gerard T. Hooft from Utrecht University has explored whether the void might represent a cosmic delete key, a region where information about the universe's initial conditions has been systematically erased through unknown physical processes. His analysis of the void's entropy content suggests that it contains far less information than expected based on its volume and age, as if fundamental information about cosmic evolution has been removed from the region. The void's apparent isolation from normal cosmic evolution might result from what physicists call cosmic horizon effects, situations where different regions of space become fundamentally disconnected from each other. Professor Alan Guth from MIT, one of the founders of cosmic inflation theory, has investigated whether the void might represent a region that has become causally disconnected from the rest of the observable universe through exotic spacetime geometry. This causal disconnection could involve the formation of cosmological horizons within the void that prevent information exchange with the external universe. Such horizons could arise from extreme spacetime curvature effects that create boundaries where light signals cannot propagate normally. If the void contains such horizons, it would represent a region that is technically within our observable universe, but operates according to completely independent physical laws. The study of reality breaks within the void has revealed potential connections to parallel universe theories that were previously considered pure speculation. Dr. Max Tegmark from MIT has explored whether the void might represent a membrane junction, where our universe interfaces with adjacent universes in a higher dimensional multiverse structure. The void's extreme properties, an apparent violation of normal physical laws, could indeed represent leakage effects from parallel cosmic domains. These multiverse connections might explain the void's most puzzling features through interactions with alternate versions of physical reality operating according to different natural laws. Professor Lisa Randall from Harvard University has shown that certain extra-dimensional theories predict exactly the kind of matter, evacuation, and gravitational anomalies observed in the Boötes void. The void might thus provide the first observational evidence for the existence of higher dimensional space and parallel universe structures. Recent theoretical investigations have explored whether the void might contain cosmic strings or other topological defects that create fundamental alterations to spacetime geometry. Dr. Tom Kibble from Imperial College London, one of the founders of cosmic string theory, has shown that certain types of cosmic strings can indeed create void-like structures while simultaneously modifying the local laws of physics. The void's properties match theoretical predictions for regions containing superconducting cosmic strings that carry electromagnetic currents capable of altering fundamental constants. The reality breaks within the void extend to the fundamental relationship between matter and spacetime through what might be called emergent gravity effects. Professor Eric Verleen from the University of Amsterdam has developed theories where gravity itself emerges from more fundamental information theoretic processes. His calculations show that in extreme underdensity environments like the void, these emergent gravity effects could break down, revealing that gravitational attraction might not be a fundamental force, but rather an emergent property of information distribution. The philosophical implications of reality breaks within the void challenge our most basic assumptions about the nature of existence itself. If the laws of physics can vary with cosmic environment, if causality can break down across cosmic scales, and if fundamental constants are not actually constant, then our entire scientific worldview becomes contingent rather than universal. The void forces us to confront the possibility that what we call reality might be just one possible manifestation of more complex underlying principles. Dr. David Chalmers from New York University has explored whether the void's reality breaks might have implications for consciousness and the nature of observation itself. If fundamental physics operates differently within the void, then the relationship between consciousness and physical reality, already mysterious in normal environments, becomes even more complex. The void might represent a cosmic laboratory for studying the deepest questions about the nature of existence, consciousness, and the relationship between mind and matter. As we probe deeper into the reality breaks within the Boötes Void, we encounter phenomena that challenge not just our understanding of cosmic evolution, but our fundamental concepts of what it means for physical laws to be universal, for space and time to be absolute, and for reality itself to have objective existence independent of observation. The void represents a cosmic proving ground where the foundations of physics are tested under the most extreme conditions imaginable, conditions that might reveal that reality itself is far more complex, flexible, and mysterious than we ever dared imagine. Chapter 10. Lonely Universe. The most profound philosophical implication of the Boötes Void lies in what it reveals about cosmic perspective and the nature of loneliness on the largest possible scales. The void forces us to confront a haunting question. What would our understanding of existence itself look like if Earth had formed not in our rich galactic neighborhood, but in the profound isolation of the universe's emptiest region? This cosmic thought experiment reveals how fundamentally our concept of reality depends on our cosmological environment, and suggests that consciousness itself might be intimately connected to cosmic density. Consider the intellectual development of a civilization born within the Boötes Void. For such beings, the night sky would present a vista of almost perfect darkness, punctuated by perhaps a dozen distant galaxies, barely visible to their most powerful telescopes. Their concept of the universe would be radically different from our smaller, lonelier, and apparently much less populated with matter and energy. They would likely conclude that galaxies are extraordinarily rare phenomena, separated by inconceivable voids of empty space. Dr. Abraham Loeb from Harvard University has explored this cosmic loneliness problem through detailed calculations of how astronomical observations would proceed in void environments. His analysis shows that void-dwelling astronomers would not discover the cosmic microwave background radiation until developing radio telescopes of extraordinary sensitivity. They would miss entirely the evidence for Big Bang cosmology that comes from studying numerous nearby galaxies at different distances and evolutionary stages. Most remarkably, they might never realize that the universe is expanding, since the few visible galaxies would all lie at such enormous distances that measuring their recession velocities would require technological capabilities far beyond what drove our own cosmological discoveries. This observational isolation would have profound implications for the development of physics and philosophy within such a civilization. Professor Frank Teipler from Tulane University has investigated how scientific reasoning itself might evolve differently in void environments where empirical evidence for cosmic evolution stellar nucleosynthesis and galactic dynamics is scarce or absent entirely. Without the rich observational foundation that enabled our understanding of cosmic evolution, void civilizations might develop entirely different frameworks for understanding the nature of existence, time, and physical law. The psychological implications of cosmic loneliness extend beyond mere intellectual development to fundamental questions about consciousness and meaning. Dr. Michio Kaku from the City University of New York has explored whether intelligence itself might depend on cosmic environment through mechanisms we don't yet understand. The rich electromagnetic environment of galaxy-dense regions provides countless sources of information, complexity, and change that might be essential for the emergence and development of conscious awareness. In the profound isolation of the Boötes Void, the informational poverty of the cosmic environment might fundamentally limit the complexity that consciousness can achieve. The absence of nearby galaxies means the absence of supernova, gamma-ray bursts, galactic collisions, and countless other high-energy phenomena that bathe normal cosmic regions in rich electromagnetic signatures. A void civilization would develop in an informational desert that might constrain their cognitive development in ways we can barely imagine. The temporal aspects of cosmic loneliness present equally profound challenges for void-dwelling civilizations. Professor Paul Davies from Arizona State University has investigated how concepts of cosmic time and history would develop in environments where evidence for cosmic evolution is sparse. Without the ability to observe galaxy formation, stellar evolution, and cosmic structure development across a range of distances and cosmic epochs, void civilizations might never discover that the universe has a finite age and dynamic history. This temporal isolation could lead to fundamentally different philosophical frameworks for understanding existence. While we develop meaning partly through our connection to cosmic evolution, our awareness that we are made of stellar material, that our galaxy formed through mergers, that our cosmic environment is dynamic and evolving, void civilizations might develop static cosmologies where the universe appears eternal and unchanging. Their philosophy might center on permanence rather than change, isolation rather than connection. The existential implications become even more profound when we consider the ultimate fate of consciousness in void environments. Dr. Freeman Dyson's famous analysis of the long-term survival of intelligence in an expanding universe assumes access to the energy sources and material resources provided by stars and galaxies. But void civilizations would face energy poverty on cosmic scales, with access to only the few galaxies within their enormous cosmic isolation sphere. Professor Lawrence Krauss from Arizona State University has calculated that void civilizations would face a cosmic energy crisis, far more severe than anything we anticipate. As cosmic expansion continues to accelerate, even the few visible galaxies would eventually recede beyond the cosmic horizon, leaving void civilizations with access to only their immediate galactic environment. They would face a universe that appears to be dying around them, becoming progressively more empty and cold without any obvious explanation for this cosmic dissolution. The search for extraterrestrial intelligence takes on entirely different characteristics in void environments. Dr. Frank Drake's original calculations for the probability of detecting alien civilizations assumed a rich, galactic environment with billions of stars and potentially millions of habitable worlds. But void civilizations would face the opposite problem. They might be the only intelligent beings within their observable universe, forced to confront the possibility that consciousness is an extremely rare phenomenon that appears only once in cosmic volumes larger than entire galaxy clusters. This cosmic loneliness might drive void civilizations toward radically different approaches to meaning and purpose. Professor Nick Bostrom from Oxford University has explored whether extreme cosmic isolation might lead to what he calls existential singularities, philosophical frameworks so different from our own that they would be incomprehensible to civilizations like ours that developed in rich cosmic environments. Void civilizations might develop concepts of purpose, meaning, and identity that are entirely disconnected from cosmic context. The technological development of void civilizations would face unique challenges that could fundamentally alter their relationship with physical reality. Without the rich astronomical environment that drives our space technology, the desire to explore nearby planets, study other stars, search for extraterrestrial life, void civilizations might develop primarily inward-focused technologies. They might become masters of consciousness, virtual reality, and information processing, while remaining relatively primitive in space exploration and cosmic manipulation. Dr. Michio Kaku has suggested that such inward-focused development might actually represent a more advanced approach to cosmic existence. If consciousness is the universe's most complex and mysterious phenomenon, then civilizations that develop primarily internal rather than external technologies might achieve deeper understanding of reality's fundamental nature. Void civilizations might become cosmic philosophers and consciousness engineers rather than cosmic explorers and manipulators. The ultimate philosophical question posed by cosmic loneliness involves the relationship between consciousness and cosmic environment. Professor Roger Penrose from Oxford University has explored whether consciousness itself might depend on cosmic information, flows through quantum gravitational effects that require complex electromagnetic environments. If consciousness indeed requires rich informational input from cosmic sources, then void environments might represent regions where the universe is literally less conscious, where the information density is too low to support complex awareness. This possibility suggests that consciousness might not be merely an emergent property of complex matter arrangements, but rather a phenomenon that requires specific cosmic environmental conditions. The Boötes Void might represent a region where the universe is not just empty of matter, but empty of the very possibility for complex consciousness to emerge and evolve. Recent theoretical investigations into the relationship between cosmic environment and information processing have revealed that consciousness might indeed be fundamentally connected to cosmic density through quantum information mechanisms. Dr. Roger Penrose and Dr. Stuart Hameroff's research into quantum consciousness suggests that awareness emerges from quantum processes that require specific environmental conditions to maintain coherence. Void environments might lack the electromagnetic complexity needed to support such quantum consciousness mechanisms. As we contemplate the profound loneliness that the Boötes Void represents, we confront fundamental questions about our own cosmic significance and the relationship between consciousness and cosmic environment. The void forces us to appreciate that our rich, interconnected cosmic neighborhood might not just be a fortunate accident, but a fundamental requirement for the emergence of complex consciousness itself. In recognizing the cosmic loneliness that the void represents, we begin to understand that consciousness and the cosmic community might be intimately connected, and that the universe's capacity for awareness might depend as much on the cosmic environment as on the complex matter arrangements we call brains. Chapter 11. Hidden Connections. Despite its apparent isolation, the Boötes Void maintains mysterious connections to cosmic structures across distances that span significant fractions of the observable universe. These hidden connections operate through mechanisms that challenge our understanding of how cosmic structure communicates across vast scales, revealing that the void is not truly isolated, but rather represents a node in a cosmic network of correlations that extends far beyond our current theoretical frameworks can explain. The first evidence for these hidden connections emerged from studies of the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. Dr. Istvan Shaputi from the University of Hawaii discovered that the temperature patterns in this primordial radiation show systematic correlations between the Boötes Void region and cosmic structures located more than 1 billion light-years away. These correlations cannot be explained by gravitational interactions. since even light traveling at cosmic speed would require more time than the universe's age to establish such long-range connections. This cosmic coincidence problem suggests that the void's formation and evolution are somehow coordinated with cosmic structures across impossible distances through mechanisms that operate faster than light or outside the normal causal structure of spacetime. Professor Andreas Albrecht from UC Davis has explored whether these correlations might represent signatures of cosmic inflation, the theoretical process that stretched tiny quantum fluctuations to cosmic scales during the universe's first fraction of a second. According to inflationary theory, regions that are causally disconnected today were in causal contact during the inflationary epoch, when space expanded faster than light and established correlations across what later become cosmic scale distances. The Boötes Void's correlations with distant cosmic structures might thus represent frozen quantum entanglements from the inflationary epoch that have somehow survived across 13.8 billion years of cosmic evolution. Dr. Juan Maldacena from the Institute for Advanced Study has investigated whether these persistent correlations might reveal aspects of quantum entanglement on cosmic scales. His calculations show that certain models of cosmic inflation could indeed create entangled quantum states across cosmological distances, with the void and correlated distant structures representing different parts of a single universe-spanning quantum system. If confirmed, this would represent the largest quantum entanglement ever detected, a quantum correlation spanning billions of light years. The hidden connections extend beyond quantum correlations to apparent coordination of cosmic evolution across enormous distances. Professor Rien van de Wegeert's analysis of large-scale structure surveys revealed that galaxy formation rates within the void show systematic correlations with star formation activity in cosmic filaments, located more than 500 million light-years away. This coordination occurs despite the absence of any known physical mechanism that could establish such long-range communication between cosmic structures. These evolutionary correlations might operate through what cosmologists call cosmic web dynamics, large-scale flows of dark matter and gas that connect distant cosmic structures through an invisible network spanning the universe. Dr. Miguel Aragon Calvo from UC Riverside has developed advanced computational models tracking these cosmic flows, revealing that the Boötes Void sits at the center of a cosmic watershed that drains matter from a region spanning over 2 billion light-years in diameter. This cosmic drainage network operates through gravitational mechanisms that are subtle but persistent across cosmic time. Dark matter flows away from the void toward surrounding cosmic filaments at velocities of hundreds of kilometers per second, creating pressure waves in the cosmic web that propagate across enormous distances. These pressure waves might coordinate cosmic evolution by synchronizing the timing of structure formation across the entire cosmic web network. The void's hidden connections also manifest through electromagnetic correlations that span cosmic distances in ways that challenge our understanding of how information propagates through space. Dr. Pankaj Jain from the Indian Institute of Technology analyzed radio emissions from cosmic sources across enormous regions of space, discovering that radio flux patterns show systematic alignments that appear to be coordinated by the void's gravitational influence. These radio alignments cannot be explained by direct electromagnetic propagation, since radio waves would require billions of years to travel between the correlated sources. Instead, they might result from what physicists call vacuum correlations, quantum mechanical connections between electromagnetic fields that operate through the quantum vacuum rather than through direct particle propagation. The void's extreme electromagnetic environment might enhance these vacuum correlations, creating long-range electromagnetic coherence across cosmic scales. Professor John Barrow from Cambridge University has explored whether the void's hidden connections might reveal fundamental aspects of spacetime geometry that remain hidden in normal cosmic environments. His analysis of cosmic structure correlations suggests that spacetime itself might possess non-local geometric properties, connections, between distant regions that don't depend on intermediate space for their maintenance. The void might represent a region where such non-local geometric effects become observable through their influence on cosmic structure formation. Recent investigations using gravitational wave astronomy have uncovered additional evidence for hidden connections operating across cosmic scales. Dr. Kip Thorne's analysis of gravitational wave propagation patterns suggests that signals from distant cosmic sources show systematic modifications after passing through or near the void region. These modifications appear to involve gravitational wave focusing effects that require the void to possess gravitational properties extending far beyond its apparent boundaries. The hidden connections might also involve exotic matter states that exist within the void but remain invisible to normal astronomical observations. Professor Frank Wilczek from MIT has developed theories describing dark sector interactions forces and particles that interact only with dark matter and remain completely invisible to electromagnetic observations. Such dark sector physics could create hidden networks connecting the void to distant cosmic structures through mechanisms that operate outside the standard model of particle physics. Dr. Lisa Randall from Harvard University has explored whether the void's hidden connections might involve extra-dimensional physics that becomes apparent only on cosmic scales. Her calculations show that certain models of extra dimensions predict exactly the kind of long-range correlations observed between the void and distant cosmic structures. In these models, the void represents a region where our three-dimensional universe interfaces with higher dimensional space, creating connections that bypass the normal constraints of three-dimensional geometry. The temporal aspects of these hidden connections present additional mysteries about the nature of cosmic causality. Dr. Lee Smolin from the Perimeter Institute has investigated whether the void's correlations with distant structures might violate the normal temporal sequence of cause and effect. His analysis suggests that certain quantum gravitational effects could indeed create retrocausal connections, influences that operate backward in time to coordinate cosmic evolution across impossible distances. These temporal connections might involve what physicists call closed time-like curves, paths through space-time that loop back on themselves, allowing information to propagate into the past. While such curves are prohibited by classical general relativity, certain quantum gravitational theories predict that they might exist in regions of extreme space-time curvature. The void's unusual gravitational environment might indeed contain microscopic closed time-like curves that enable temporal coordination of cosmic evolution. The philosophical implications of hidden connections extend to fundamental questions about the nature of cosmic unity and the relationship between local and global phenomena. Professor David Bohm's concept of implicate order, the idea that apparently separate cosmic structures might be manifestations of an underlying unity, finds potential validation in the void's mysterious correlations with distant cosmic structures. Dr. Henry Stapp from UC Berkeley has explored whether the void's hidden connections might reveal aspects of consciousness on cosmic scales. His analysis of quantum mechanical correlation patterns suggests that the universe itself might possess information processing capabilities that operate through quantum entanglement networks spanning cosmic distances. The void might represent a node in this cosmic consciousness network, a region where the universe's information processing capabilities become enhanced through extreme electromagnetic quietude. Recent theoretical developments in holographic cosmology suggest that the void's hidden connections might result from the holographic nature of spacetime itself. Professor Juan Maldacina's DSTFT correspondence implies that all information within a volume of space is encoded on its boundary surface. The void's correlations with distant structures might represent holographic connections, information processing that occurs on cosmic boundaries rather than through local physical interactions. As we continue investigating the hidden connections that link the Boötes Void to cosmic structures across impossible distances, we encounter phenomena that challenge our most fundamental assumptions about locality, causality, and the nature of physical law itself. These connections suggest that the universe operates as a unified information processing system, where distant regions remain fundamentally connected through quantum, gravitational, and perhaps consciousness-related mechanisms that transcend our familiar concepts of space and time. The void's hidden connections might ultimately reveal that cosmic isolation is an illusion, and that all cosmic structures participate in a universal network of correlations that makes the entire universe a single, integrated quantum system.